Example 4.3. Determine the current through the 14 ohm resistor using a Thévenin equivalent circuit, using both methods. So the current through the 14 ohm resistor always flows from A to B. In other words, when I look at this current has to be flowing in this direction right here. So in order to determine this using Thévenin's equivalent, I need to remove the 14 ohm load and simplify the circuit if possible. So if I look at the left side where the 9 ohm and the 8 volt source are, we see here is that we're going to use source transformations starting from the left. So if I look at the circuit, that circuit looks something like this here. So I see here that I have a 9 and I have an 8 that are in series. And so it is this branch that I'm interested in simplifying. So if I simplify this guy, you could then see that this now becomes the Norton resistance, which is still 9 ohms, and then I'm going to get a parallel current source. So if I get a parallel current source, that's going to be 8/9 of an amp. So if I look at the circuit, this now tells me that I can redraw the circuit, and it looks something like this. I'm going to have a 9 ohm. I'm going to have an 8/9 amps. But now the circuit has a 2 amp source that looks like this. So then I have my 6, then I have another 10. So here's my 10 ohm, here's my 6 ohm, and then of course I have my 20 volts right here, and then I have my 4 ohm right here. And again, since I removed it, this is AB. So you can see here is that what I'm going to do now is that I'm really looking at this branch right here, and I'm going to simplify that branch. I'm going to make that into a voltage source and a resistor in a series here. So if I do that, I now have this thing. So if I continue with my source transformations, I now see that I have look at the circuit now. I have a 9 and a 6 in series. So that's going to give me 15. And then I have to add these two current sources together. Now note that the current source is going to be going down, the effective current source. So here I go. So if I do that, I'm now going to get a circuit that looks something like this. So if I do that source transformation, you're going to see that now I have a voltage source that should be pointing down, and it turns out to be 10 volts. And then I have my 9, and then you could see here is that then I have my 6 here. And then if I continue to move going to the right, you know that that's my 10 ohm. And then I have my circuit, which has my 20 volt my 4 ohm, and then here's my nodes A and B. So now I'm going to say that if I continue to simplify the circuit, you could see here that now I have a source like this and one resistor. I'm going to say that this is my final circuit. So I will not deal with the original circuit. I'm going to only deal with this circuit because I've simplified it. So this is the circuit I want right here. So when I solve any circuit, this is the one I want. So that's the equivalent here. So now what am I going to go do? I'm going to go calculate VOC. So the first thing I need to do here, I want to determine VOC. Now, when I look at VOC here, one of the things here is that, again, this is my circuit right here. This is the one I'm going to be dealing with right here. So what you're seeing here is that the way we've set this up, note that this is my plus, that's my minus, and this is VOC. So when I look at this circuit for VOC, I cannot ignore that 20-volt source because it's an open circuit here. So one cannot ignore the 20-volt source in the open circuit. But the 4 ohm has no voltage slash current through it. So that means here it's a dead resistor. Now, because this is, this is an open branch here, what you're seeing here is that my current only flows in this branch right here. So that means that if I look at this guy, that's going to be the polarity right there of that 10-volt source right there. So I really only have one circuit to analyze. So here's what I'm going to see here. So if I look at KVL, so KVL around the open. Now remember, this resistor is dead because it's open. That tells me that, so if I look at my polarity, if I'm going down, you could see here that I'm going to get positive VOC, positive voltage across the 10, positive 20, and that's equal to 0. So you could see here is that VOC is then going to be minus V10, minus 20. So right away, our focus here is to solve V10. So remember, this is going to be V10 right there. But I only have one loop. So then what I'm going to do here is that I'm going to solve the single left loop to get V10. So if I look at that circuit, it looks something like this. Right, so there's my 10 volt. I have 2 resistors in series. So I could see here is that this is my 10 ohm. And then according to what we said here, that has to be V10. And then this is a 15 ohm resistor. And of course, we could see here is that the current has to be moving in that direction. So I'm going to use VDR to calculate V10. So then V10 is then going to equal to 10 plus 15, 10 times 10 volts. And you see this is a positive 4 volts. So now that I have that, I can now calculate VOC. So then VOC is going to be minus V10 minus 20. And you can see here is that's 4. That's going to give me minus 4, minus 20, minus 24 volts for VOC. So for method 1 and method 2, we get the exact same process of calculating VOC. So now how the two methods vary is that we have to calculate the resistance. Okay, so now here we go. So now we're going to go to step 2. And we want to determine RTH. And we're going to use two methods. So the first one I'm going to use is that I'm going to use method 1. And method 1, what you do here is that you have to deactivate all sources. So if I do that, remember, I have only one circuit. So if I look at that, there's my circuit right there. So what I'm going to do now is that I'm going to deactivate sources. And when I do that, you can see here is that I now have a short here. I have this resistor right here. I have a 10. That 20 volt source right here gets shorted out. And then I have my 4 ohm resistor. So here's my A and here's my B. And so what we want is we want RTH in this direction, where this is a 15, 10, 4 ohm. So the key thing to understand here is that, look at this guy right here. The 4 ohm is present since it contributes to the effective resistance seen from the load. Now, the way we want to look at this thing is that I would look at it in this way here. So I imagine that I put an ohm meter right here, and then I'm going to let the current come in here, and it's going to come back out like that. So if that's the case here, what I'm going to do now is that I'm going to go calculate RTH. So now I'm going to calculate RTH using resistor reduction. So I could now see here, so if I follow the current, you could see how it enters the 4, and then it splits between the 15 and the 10, and then it recombines to get to the B node. So then that means here that RTH has to be 4 plus 10 parallel to 15. So we could see here is that if you multiply them and divide, you're going to get 6 ohms. So therefore, this guy's going to be 10 ohms for RTH. So again, as we've already stated, but we should say it again, what does this resistance value mean? Well, what it means here is that when I look at my circuit, it's going to look something like this. So I'm going to have a 15, I'm going to have a 10, then I'm going to have a 4. So when you're looking between A and B, what you're actually seeing here is that as you look from the location of the load, so if you're an observer from this location here, the RTH value is the resistance the observer feels. Now, the word feels is an odd one, but feels between points A, B. It's the effective resistance the load sees. And in this case, the effective resistance is 10 ohms, right? It's a combination of these resistors. So if I now put this all together here, we now see that R Thevenin equivalent, right? Our Thevenin equivalent circuit is here. Let me see if I still have a copy of that guy. Oh, I do. Good. Here's my Thevenin equivalent. That's my circuit right there. So my Thevenin equivalent is then going to be VOC, which is minus 24 volts. And then I have a Thevenin resistance, which is 10 ohms. And I can replace this circuit by that circuit. So this circuit right here, right? So this is my Thevenin equivalent. And I would say that this circuit conceptually and mathematically is equivalent to the original circuit. And you could clearly see that it's much easier to deal with than the circuit on the left. Okay, so let's calculate this guy now. Let's look at method 2. And here we're going to calculate RTH, where we're going to take the ratio of VOC times I short circuit. So what we got to do here is we got to do the same thing as before. So now what we're going to do is that we're going to place a short between AB and calculate I short circuit. So if I look at my circuit, it's got to look something like this. So here's my circuit, and I know that this is 20 volts. And if I take out my A and B, that means here, this is my I short circuit right here. Now note, I short circuit is going to be the same as the current through the 4 ohm resistor. So you got to remember, the current always flows from A to B. So now what we want to do here is that we want to go in and we want to calculate this current. So the question is that how do we calculate this current? So I would say that there are many ways to determine I short circuit. You could use source transformations, you could do mesh, you could do node. You should choose the method that best suits you. Now, what I'm going to do here is that the thing that sticks out the most to me is that I would do right here is that I would switch the 20 and the 4 ohm so that the 20 is now connected to this bottom line that I'm going to define as the ground. So in other words, I would switch the locations of the 20 volt with the 4 ohm. So if I do that, here's what I get. I have a 10 volt. Here's my 15. And then here's my 10. And then look what I'm going to do. I switch their locations. And then I have my 20 volts right here. So if I do that, there's some simplification here. I could see here is that now I have a common ground right here. So that means I know what this node is right here. That node is minus 10 volts. And I know what this node is right here. That guy is plus 20 volts. So the only unknown node that I don't know is this guy right here. And what I'll do here is that for the lack of I'm just going to call that Vx. So I could see here is that if I want to calculate I short circuit, I know that it's this current I short circuit that I'm looking for across that 4 ohm resistor. So what I'm going to do here is that I'm going to use node to calculate Vx. So I'm going to use node to calculate Vx. And then I'm going to use ohms to get I short circuit. So I really have two equations, two unknowns, if I could say it that way. So here we go. So if I look at node, so I'm going to look at node Vx. So then I see that that's going to give me what? 15 plus 10 plus 4. That's got to be Vx. And then I have a mutual with the 10. So I'm going to get minus 115 minus 10. And then I have a mutual with the 20. And that's equal to 0. But note, I only have one equation here. So then this tells me here is that Vx ends up being 10.4 volts. So I now have Vx right there. So now I'm going to use Ohm's law. So I'm going to come over here and I'm going to say I'm going to use Ohm's law for I short circuit. But now I know what Vx is. So Ohm's law tells me that I short circuit should be the voltage across the 4 ohm divided by 4 ohms. But that's got to be Vx minus 20 divided by 4. And if I punch in my numbers, I'm then going to get minus 2.4 amps for I short circuit. So now I have I short circuit. So now if I go and I calculate the resistance, right? So then the Thévenin resistance is then going to be what? It's going to be RTH, which is going to be VOC, I short circuit. So I'm going to get minus 24 volts divided by minus 2.4 amps. And we get positive 10 ohms for RTH. So what we're seeing here is that both methods calculate the exact same RTH value. So now I have my circuit here. So now to calculate the load current, we use the Thévenin equivalent circuit. So if I look at my circuit again, right, here's my original circuit. And so now what I'm doing here is that I still have my nodes A and B here. Now I'm going to come in and I'm going to put my load resistor back in. Right, that's that 14 ohm. And our whole goal is to calculate this current of the 14. But that's not what we want. We want to use the equivalent circuit, which looks like this. And clearly, this is much easier to deal with. So now that I have it back into the circuit here, so now I'm going to use Ohm's law to calculate the current. So I'm going to use Ohm's law, and that tells me that the current of the 14 ohm resistor, not that these guys are in series, well, I have a negative voltage source, and I have two resistors in series. And when I compute that, I get minus 1 amp for the 14 ohm resistor. And you could see that the current is not going down, it goes up for the circuit here.